Well, now our discussion will start right from atoms and nuclei, and we are going to discuss about the concepts of the radioactivity. It's a very special phenomena which normally all elements do not exhibit. There are some special type of elements which exhibit the phenomena of radioactivity. So first of all, it is very important to remember that radioactivity is a phenomena in which radiations are given out from an unstable nucleus. And all such nuclei which emit radiations in their normal state are supposed to be the natural radioactive elements. When we speak of unstability, and normally we are concerned with the neutron-proton ratio, for the radioactive elements, whether they are natural or synthetic, their neutron-proton ratio is about 1.5 and their binding energy per nucleon is less than 8 MeV, dropping towards 7.5 MeV. Another thing is that their shape is generally elliptical, that is recognized from the spectrum analysis. And another thing is that most of the radioactive nuclei, they are dominated by repulsive nuclear forces. That is, the separation among the nucleons in these nuclei is less than 0.5 Fermi. So these are basic concepts which are showing the instability of the nucleus. So radioactivity is a spontaneous phenomenon, not affected by temperature, pressure, or density variations. And most of the laws of radioactivity, they depend upon the chances and probabilities. We find that in case of a radioactive element, the decay or the disintegration is a matter of chance. When the particular nucleus will start decaying cannot be predicted. However, once it will disintegrate, we find that disintegrations continue between 0 and infinity. That is, disintegration or decay may stop any moment between 0 and infinity, or it may continue right up till infinity, cannot be exactly predicted. Moreover, during the emission of particles, we find that alpha and beta emissions depend upon chance. There is no definite law which predicts that when alpha emission will take place and when beta emission will take place. However, one thing is very clear, whether it is alpha emission or it is beta emission, gamma rays are always generated from a radioactive nucleus. And another thing, period of disintegration varies from 0 to infinity. If atomic numbers of the elements are from 82 to 92 and mass numbers from 206, or you can say that is we are referring to lead isotope. So atomic number must vary from 82 to 92 and mass numbers vary from 210 to 238. All these elements are supposed to be the natural radioactive elements. Their atomic numbers vary from 82 to 92 and mass numbers vary from 210 to 238. However, 82 is the atomic number of lead, and lead isotope with 206, 207 and 208, they are the stable isotope. But other isotopes like 210, 212 and 240 are unstable. They are natural radioactive. And if atomic number exceeds 92 and mass number exceeds 238, then they are supposed to be synthetic radioactive element, artificial radioactive element, or the transuranium element. Well, whether they are natural radioactive elements or synthetic radioactive elements, the common tendency is that they always emit alpha, beta, and gamma radiations. But one thing is very important, that alpha and beta emission is never simultaneous. They are one after the other. Either alpha emission is followed by beta or beta emission is followed by alpha. Now, let us suppose that alpha and beta emissions are simultaneous. However, we know that the simultaneous emission is not possible. But if we assume that alpha and beta emissions are simultaneous, there will be interaction among the positive helium nucleus and negative beta particle. As a result of interaction, a new nucleus will be formed whose atomic number will be 1 and mass number will be 4. That is, we expect a hydrogen nucleus with 1 atomic number, which is true, but mass number 4 is not expected because we expect that there are only 3 isotopes of hydrogen, that is the protium, deuterium, and tritium. That is 1H1, 1H2, and 1H3. So 1H4 is not reported and in any of the nuclear phenomena. So we don't find that alpha and beta emission interact. It means either alpha will be followed by beta or beta will be followed by alpha. However, gamma rays are always generated. Now, another important thing, that is the magnitude of radioactivity. We will remember like this, that radioactivity is a phenomena in which radiations are given out from an unstable nucleus. And mathematically, the rate of disintegration of a radioactive sample decides the radioactivity. Larger the rate of disintegration, larger will be the radioactivity of that sample. So if we assume that Dn atoms disintegrate in dt time, then the rate of disintegration will be dn over dt, and dn over dt will be proportional to n, where n is the number of atoms in time t, or dn over dt is equal to minus lambda n. Negative sign indicates that as the disintegration goes on increasing, the number of atoms will go on decreasing, and lambda is called the decay constant or disintegration constant. It is different for different radioactive samples. Radioactivity is generally expressed in terms of Rutherford, Curie, and becquerel. The basic unit is becquerel. 1 becquerel is 1 disintegration per second. That is, if 1 atom or 1 nucleus disintegrates in 1 second in a radioactive sample, the radioactivity will be 1 Curie. Similarly, 1 Rutherford means 10 to the power 6 disintegrations per second, or we can say 1 Rutherford is 10 to the power 6 becquerel. And the third one is, that is the biggest unit, that is Curie. 1 Curie is generally 3.7 into 10 to the power 10 disintegrations per second. We can convert it to Rutherford also. But 1 disintegration per second means that is 1 atom or 1 nucleus breaking per second. So rate of disintegration of a radioactive sample decides whether radioactivity is more or less. So most of the laws of radioactivity depend upon the chances and probabilities. But there is some definite law also, and this definite law is called the group displacement law. According to the group displacement law, we find that when alpha emission takes place from a radioactive nucleus, a resultant nucleus is generated whose atomic number reduced by 2 units and mass number reduced by 4 units, and a new element is formed. Similarly, during beta emission, a new element is formed whose atomic number increased by 1 unit and there is no variation to mass number. Now, these facts are to be applied in the radioactivity, and there are various radioactive series also. And in the radioactive series, normally we have uranium series, actinium series, then neptunium series, all these types of series. So there are some natural series and some artificial series. So another important thing regarding the radioactivity, that only group displacement law is the definite law. And this phenomenon was first explained by becquerel. It was later on further modified and explained by Curie after the discovery of radium. Now we come towards the main concepts. The general equation of the radioactivity is n is equal to n naught e to the power minus lambda t, where n is the number of atoms in time t and n naught is the number of atoms at t is equal to 0, where n naught is the original number of radioactive atoms N is less than N naught, and T is greater than 0. And then by exponential equation, we find how the atoms are decaying. Normally from exponential graph, we find that time is taken on the x-axis and the variation in the number of atoms that is taken on the y-axis. In this context, we define the half-life period, and the half-life period is the time in which half of the radioactive atoms disintegrate from the sample. And when we use the term average life is the reciprocal of decay constant. Average life is normally 1 over lambda, whereas half-life is 0.6931 over lambda. And if we divide average life by half-life, the ratio becomes 1.44. So average life is about 1.44 times the half-life period. So these are the various concepts, and in certain cases we have to drive the formula, but with the competition point of view, what we find, we have to apply the formula, not to drive the formula. We have to apply them in the various questions. So now we come towards radioactivity, the main procedure, main concepts. The radioactivity, the introduction is regarding the Becquerel. The phenomena of radioactivity was discovered by Henry Becquerel in uranium salts in 1896. He found that in the dark, the salt begins to glow. So that is exhibiting that some radiations are given out. That was the primary investigation by Becquerel. After the discovery of radioactivity in uranium, Pierre Curie and Madame Curie discovered a new radioactive element, that is radium, which is about 10 to the power 6 times more radioactive than uranium. Radium was extracted from pitch black, most probably the ore of zinc, a kind of coal tar, for which Curie's were honored by Nobel Prize in 1903. So, as I have explained earlier, that it's a spontaneous phenomena, that is radioactivity is a spontaneous phenomena. So, the self-spontaneous disintegration, that is decay of unstable radioactive nuclei, is known as radioactivity. The nuclei exhibiting this phenomena are known as radioactive nuclei, and the procedure is not affected by temperature, pressure, and density variations. Some examples of the radioactive substances or elements are uranium, radium, thorium, polonium, neptunium. In all these cases, you will find that neutron-proton ratio is generally 1.5, and we find that their shapes will be, nuclear shapes will be elliptical. And that's another important thing about these elements, these nuclei, and their binding energies per nucleon are less than 8 million electron volts, dropping towards 7.5. And all these nuclei are dominated by the repulsive nuclear forces, because the separation among the nucleons of these nuclei is less than about 0.5 Fermi. 1 Fermi means 10 to the power minus 15 meters. All elements having atomic number greater than or equal to 82 are radioactive elements, but mass number is very important. That is from 210 to 238, then they become the natural radioactive. And if atomic number is exceeding 92 and mass number exceeding 238, then they become transuranium, artificial radioactive elements. In case of lead, there are 6 isotopes, that is 206, 207, 208. They are stable, but other isotopes like 210, 212, and 214 are unstable. So lead with atomic number 82 is the most stable element. In the high atomic number elements, that's why all radioactive elements emit radioactive radiations till they are converted into lead. 206, 207, 208 stable, and 210 unstable. Radioactivity is a nuclear event and not atomic event. So it is the decay of a nucleus, not the decay of an atom. Hence, electronic configuration of atom don't have any relationship with the radioactivity. Decay process are random. When it will start decaying, when it will stop cannot be predicted. Here one simple knows that in radioactive element, radioactivity is taking place, or it is definite that a certain number of atoms will decay in a given time interval. But one never knows that which particular radioactive nucleus will decay and when it will decay. It is just a matter of chance. That is probability. I have already explained it, which is explained by the quantum mechanics. It is statistical in nature. This process is spontaneous. It can either be started, stopped, accelerated, nor retarded by any physical phenomena, like by changing temperature, pressure, or density, or any chemical change. All these facts I have already spoken, and now we are just having the main concepts regarding that. This phenomena, parent-daughter chain continues. Original radioactive elements are called the parent elements or the nucleus that new elements is called the daughter element or disintegrated nucleus. Like for example, a few points are indicated here in this equation. However, if this equation continues like 92 uranium 238, its tendency is to give out alpha particles. So here we can apply the group displacement law. A new element will be formed called a daughter element, whereas uranium 238 will be known as the parent element. And this 90 thorium 234 is produced after the emission of alpha particle. However, the tendency of thorium 234 is to emit a beta particle. So atomic number will increase to 91, mass number will remain same, and this element is called protoactinium, and protoactinium is a daughter element, whereas thorium will be parent element. If this series continue, like protoactinium, it is tendency of generation of beta particle, so obviously we will get 92 uranium 234, so this is also one of the isotope of uranium. Like this, the series continue, and finally uranium 238 series end at 82 lead 206, that is a stable isotope of lead. So now we come towards in the radioactive phenomena, alpha, beta particles and gamma rays are emitted, whether they are natural or synthetic elements. For a given nuclei at a particular time, emission of either alpha or beta takes place, never both at a time. I have explained earlier that if they are emitted both at a time, we expect a fourth isotope of hydrogen with atomic number 1 and mass number 4, and that is not possible because we detect only 3 isotopes of hydrogen, that is 1H1, 1H2 and 1H3. That's why both emissions are never simultaneous. Due to emission of alpha, beta and gamma radiations during radioactive decay, the mass of the parent nuclei goes on decreasing. So mass is decreasing means if alpha emission. But if beta emission takes place, obviously there is no variation to mass. However, atomic number will vary. In case of beta emission, atomic number increases, no variation to mass. And in alpha emission, both atomic number and mass both will change. And for gamma radiation, we find that there is no variation to charge and mass.